Hello, in this video I'll be talking about 4.4, systems of equations in 3 variables. So we recently saw systems of equations in 2 variables, right, x and y, and that puts us in a 2-dimensional zone, right? When we're graphing stuff like that, we end up in this 2D world. Right, we have a line going here, a line going there. I'm thinking of stuff like this, where we had like x plus y equals 10, and like negative 2x plus y equals 3, right? These types of systems would result in these types of geometries, and sometimes they would have solutions. Sometimes they wouldn't. The solutions therein would be called ordered pairs, x, y, right? Some distance over to the right and some distance up. That's why we call it 2D. Now we're adding in a 3rd dimension. So imagine there was an axis coming out of the page, right? A z-axis coming out of the page. And now we have a space rather than just, this area. So rather than having lines, you have actually what are called planes. I tried to draw something there, but you can think of them kind of as sheets. There's a picture at the bottom of the page kind of some particular orientations of these planes for different systems. So you kind of have to make analogies between the geometry that was happening in 2D and attempt to connect those geometries to the ones that are happening now in 3D. It can be helpful because there are specific connections. So let's look at what it means to be a solution to a system of 3 variables. Keep in mind what it meant to be a solution to a system of 2 variables, right? So if I plug in a point and I get a true statement in each, then that point would be the solution to this system. We would call that an ordered pair. Here it says show that the ordered triple, right? Ordered triple. So it says -1, 2, -2. So now this is x, this is y, and now this is the z component. So to show that this is a solution to the system, I actually need to plug this in everywhere. And then make sure that we indeed get true statements everywhere. So I'll go ahead and do that. So we'll have -1 plus 2 times 2 minus 3 times -2, question mark, are you equal to 9? And then I'll plug this point into the second equation. Is it true that 2 times -1 minus 2 plus 2 times -2 is equal to -8? All right, I'm plugging in this point to all 3. Is it true that the opposite of -1 plus 3 times 2 minus 4 times -2 is equal to 15? Okay. Feel free to grab the calculator, right? Of course. So -1 plus 2 times 2 minus 3 times, looks like I hit 2 actually, didn't I? So minus 3 times -2, this should be a 9, good. So this one's true. 2 times -1 minus 2 plus 2 times -2. That should be a -8, and it is. -1 plus 3 times 2 minus 4 times -2. This should be a 15, good. So if any of those were false, then this would not be a solution. So yes, solution, right, shown. Okay, So we had a solution. Not in every system do you have solutions. I think we've seen that. And not in every solution, or sorry, not in every system of these types of planes do we have solutions either. So we're used to kind of thinking of lines intersecting, right? That's what we've been doing. What I'm saying now is we actually now have a third dimension, which implies that these are now planes in 3D rather than just lines in 2D. Let's look at these hypothetical orientations. So this is meant to be like a system of parallel planes, if you will, right? We're used to, like if we have a graph and we have these two, what I'm trying to draw are parallel lines, they won't have a solution. Parallel planes also don't intersect anywhere, so they won't have a solution either. If you consider an orientation such as this, right, 3 planes in a system such as this, well, you would have infinitely many solutions, actually, right? Along this entire line are intersections of all 3 planes. So you would have infinitely many. So you have 0 here, you have infinitely many here. Here's another orientation of 3 planes. Remember, to be a solution, you have to be a point on all 3 planes simultaneously. Nowhere in this orientation is there a point that's on all 3 planes, right? All these points are on just these 2 planes, and then all these points are on just these 2 planes, and nowhere does there exist a point that's on all 3. So this would have 0 solutions, actually. This orientation, another kind of interesting configuration there of 3 planes. A solution has to be on all 3 planes at the same time, and there is no such point, right? These infinitely many points are just on these 2 planes, right? This plane is not involved at all. And then this line involves just these 2, and this plane over here is not involved at all, and so on and so forth. This would actually have 0 solutions. Here, this point right in the very middle, I could argue, and you might be able to agree that would be on all 3 points, right? All 3 planes, that is. So this would have exactly 1 solution, that hypothetical system. Anyways, I know that's conceptual. Let's solve one. Well, let's do at least 2, actually. All right, so here it says solve the system using the elimination method. So yeah, it's very similar to what we've been doing. It's really the same methods, but we're extending those into this 3D situation. So you could use substitution here, but we're specifically being asked to use elimination, so we're kind of stuck. So what we want to do is add, and we want the result of that addition to lead to cancellations, right? So we get eliminations, and this reduces our system. So I'm trying to find a combination of equations that is nice to work with, right? That leads to a lot of cancellations. And it looks like if I take the first one and the second one and add those just as is without altering anything, we'll get 3x. The y's actually cancel. The z's actually cancel. And we just get 3x equal to 9. Really quick. I can divide by 3, and now I know x, just like that. Okay. So you can now replace x everywhere. if you wish. You know x, so you can say that. You can say this. Right? Everywhere you have an x, you now have a 3 if you wish. So if I do that, that would just leave y and z. So if I subtract over this 3 in all cases, or this 6 in this case, right? So I'm subtracting over 3 now, here and here. And I'm subtracting over a 6 here. So this system would now lead to y plus z equals 3. Negative y minus z equals negative 3, which is actually the same equation as this one. And then we would have negative 2y plus 2z equals 10. Okay, so I'll work with these two, maybe now, I'll work with these two and try to learn y and z, right? We already know x, so now I just have a system of two unknowns with these two equations. I'll just look at these two and I'll try to learn what y and z are from them. So it looks like I have a negative 1 and a positive 2 as the coefficients on z. So I can make a negative 2 here. So how do I make a negative 2 here? What number do I want to multiply through by? I'm going to choose a 2. Right, I'm just trying to decide where to put that 2. So I'll just try to sneak that in. That's a 2. So this would now look like negative 2y minus 2z equals negative 6. And then down below we'd have negative 2y plus 2z equals 10. Then when I add, I get the z's to go away. So negative 4y equals 4. Divide by negative 4. So y apparently is negative 1 from that work. Y is negative 1, so just looking at what we have to work with, I could now take that right here and learn what z is. So if I do that, I know negative 1 plus z should be 3. So add 1. So it looks like z is 4. So I would have an ordered triple as the potential solution here. So I'd have in the x location 3, I'd have negative 1, and then 4. Right, x, y, z. Let's check that. So 3, negative 1, and 4. So 3, so for the first one we'd have 3 plus negative 1 plus 4. Is that equal to 6? If this is true, I leave it to the rest. You know, I leave it to you to check the rest of them. So 3 plus negative 1 is 2. 2 plus 4 is 6. Yeah, so this is a good indicator. But you do need to check the solution in all three. I've just checked the first one. It needs to be true for the rest to be the true solution. I'm going to solve another one of these. This one just says solve the system. So I'm going to choose to do this a different way, just to kind of introduce another way. I'm going to go back to substitution. So let's see, just to make a choice, So I'm kind of considering what to do. I want to make a system. So I want to, just to tell you what I'm thinking about, I want to convert this. Let's just go ahead and convert it into something just with x's and y's, right? Let's kind of use substitution to take this thing down a notch and go just to x's and y's. So we'll eliminate z, in other words. So I'm noticing that if I add z, that I can say that 2y is equal to z. So wherever I have a z, specifically here and here, right? So just notice, so I'm working with the third equation, right? I developed a new relationship, and then I'm plugging that into the others. So if I do that, then we'll get x plus y plus 2y equals 180, and then x minus 2y equals negative 70. And here is something involving just x's and y's now, right? That's what I was talking about over here. So I, through substitution, have reduced the system from 3 unknowns down to 2 unknowns. Combine like terms. So x plus 3y equals 180. And yeah, up to you how you continue this. I'll go ahead and continue with substitution though. So I'll add 2y. So bringing that all the way over here actually. So x in that second equation would be equal to 2y minus 70, right? If I add this 2y over. So I can go ahead and use this in replacement of x here. So I'll write 2y minus 70 in replacement of x here. So I'm using substitution again, right? So I used substitution once, it gave me this, but now I want to go from this down to just x or y. So I'm just kind of whittling it down. So it takes patience and attention to detail, I would say, or else mistakes will just happen a lot. So I'm plugging into here, and then I'm adding 3y equals 180. Combine like terms. So 5y, and then maybe I'll add 70 at the same time. Running out of room there. So 250 divide by 5. So it looks like 50 for y. Cool. How do I find, let's say, z? Well, this thing says if you know y, then you know z by doubling y. So I know z would be double, 2 times y, 2 times 50 is 100. Just looking around at kind of useful bits of information, the first equation says x plus y plus z equals 180. And I know that y is 150, or sorry, y is 50, z is 100. That means y plus z is 150. So that means x needs to be the amount. Hey everyone, looks like the video cut off for some reason, but I was just saying, once you have y and z, you can kind of be as clever as you wish, right? You can look around and say, okay, what do I know? Well, we know x plus y plus z is 180, right? And if you know y and z, then you essentially know x, right? So if y plus z adds up to 150, and we know x plus y plus z adds up to 180, then we know that x must be contributing 30 more. So we get this as a solution just written separately, or you can write it as this ordered triple. Okay, have a good one. See ya.